It's a pleasure for me to present this speech. I would like to present something as new, is brand new, and now becoming very hot field. I think we have participated to the field that becoming a little bit hot by using what we call it Ququarts. That means no more qubits, but Ququarts. Ququarts, that means 4-level system. Here, I will begin, my presentation will be about universal quantum computation using symmetrical Ququarts. So this work was done in collaboration with Professor Michael Hilke from Michael University and Professor Richard Mackenzie from University of Montreal and Dr. Christian Poudrou, Royal Military College. This was also part of the subject of the PhD of Christian, and we spent also more than 3 years to work in this subject. That's a little bit dense. I will try to select some part of it and to simplify and to give you an idea what is going on in the future of quantum computing. So, the physical, as you know, the physical realization of quantum computer is a major challenge. You know, the most building blocks of quantum computer are based on qubits, which are quantum two-level system. And then many different types of qubit have been developed, mainly using semiconductor technology, quantum dots, including silicon. As you can see here, for example, this is programmable 2-qubit quantum processor in silicon. Also here, people use quantum dots, including GIS technology, to realize 3 qubits. You can see here the first, the second, and third qubits using quantum dots to realize these qubits. It's mainly like a computation or quantum computer with 3 qubits using the GIS. And mainly the most famous part of the quantum computer or qubits, the qubits they use it is the IBM quantum computer using what they call it transmon. On transmon or fluxion or flux qubits is usually they are superconductor based on Josephson junction, and they have they are the same physics almost with different coupling. They are almost the same with different coupling. That's the difference between them. And they are now very hot components, if you want to say a very hot field, and people who are working to develop more and more qubits on stability of qubits in this here, but it's very, very sensitive to the temperature. Mainly when you have superconducting qubits, you need helium temperature. That means few Kelvin on below than that. So there is possibility. Other possibility is the possibility to realize qubits only from optical components. And this was done, for example, you see here the PNAS, and you see here this system here. Sorry for that, maybe but here. PNAS, you can see here, this system here is just 2 qubits realized to realize teleportation. And people are using trapped atomic ions as a qubit. More than that, people use it NV center in diamond. That means here you have, you know, diamond is based on carbon, structure of carbon, but sometimes the carbon is missing. And this is what we call it bad quality for the diamond. If you buy something for diamond, be sure that it's not a lot of vacancy seat there. Other way, it's just very bad quality. And then after that, is also nitrogen can be included here. And we have with this bad diamond, if you want, bad quality of diamond, we are able to realize qubits. And this has very, very nice structure and very nice properties. So all these systems that I present on others share the same basic principle of operation as they operate as a quantum two-level system. You have, if you see the atoms, ground state, excited state, if you see photons polarized, horizontal, vertical polarized, and so on. but always we have two possible states, different states, we can combine them. Okay, one of the biggest problems for quantum computation is to keep the error rate low for each quantum operation. Suppose that you want to have a quantum computer, what we do usually? We do calculation on if you do every calculation with a high rate, error rate, then after sometimes you get very wrong results. You should try to reduce as much as you can the error rate so that you can do the calculation with some confidence that your calculation is correct with high probability. This error can be originated from precision of quantum manipulation. For example, if you use qubits, solid qubits, that's a sweeping of the gate voltage. If you use, for example, qubit based on optical qubits, this laser pulse is very important. The duration of laser pulse, change of the duration pulse, and etc. in optical scale. This can generate what we call it error, but this could be assimilated to the classical error. In addition to that, this is what we call it quantum error or quantum noise. This quantum noise is intrinsic. Whatever you can eliminate all this error. Whatever you can do with precision, you can eliminate all the errors that I mentioned before as classical, but you cannot eliminate intrinsic decoherence. The intrinsic effect, which is the decoherence. This intrinsic effect, which is the noise, quantum noise, or the decoherence, is inherent to the system, is the feedback from the system coupled to the environment, is somehow the channel that the torque between the environment on the system. You cannot eliminate it, but with some tricks you can manipulate it. And this is somehow is the feedback from the environment to the system that you can understand in this sense. Source of decoherence is, as you understand, the environment. What is the environment? Environment is something that is linked the system to the outside. It can be leads, nuclear spin, optical absorption, phonon, and so on. So the idea, if the two-level system is noisy, can we go with multi-level system? Maybe we can reduce the noise. And maybe the symmetry can help us to do more. And if so, how we will do that? This is the subject of this research that I am presenting here. I would like to show you that with multi-level system on symmetry, we can do better than with qubits, normal qubits. So let's consider the physical system. Very simple system here. So let's suppose the following. Let's consider a physical system formed by, say, 4 quantum dots. But it's not obligation quantum dots, because this is concept. It can be anything. The most important thing that we have 4 sides. Okay. And then here, each one has an energy. It has energy. The seat have energy, and they are coupled to each other. You can see that they are coupled to each other and coupled to the leads, which model the environment. Okay. It's like a cable, if you want, or an ensemble of channels. So the Hamiltonian of the system is decomposed by 3 parts. The first part describing the system, or the core of the system, which is formed by 4 dots. You can see here, this is these 4 dots. I don't know if I am able to do something. Yeah, because this. Okay, you can see this is the 4 dots. And this is describing the Hamiltonian with this part here. And that is the interaction between the dots on the leads for each one. And this is the second term. And the third term is the interaction between the spins on the leads. Okay. So as I told you, we can consider this system here, this core system, we can call it transistor. I will tell you why we call it transistor, but just because this is 4, but you will see that it's really, it's very important. It's the basic of all quantum computation that we will do. So we will consider a particular scheme with the geometry symmetry. So suppose that you have a symmetry. On this symmetry is a rotation. If the system has the same parameter here, if you rotate with 90 degrees, 180 degrees, 270 degrees, 360 degrees, we have 4 possibilities. In that sense, you will not remark the difference if the system is exactly the same. We call this omega rotation invariance. Okay, on omega indicating the angle, if you want. So if we make this omega is linked to the 4th root of the 1. So we have 4 possibilities. As told you, as exponential e phi over 2 multiplied by n, or 0, 1, 2, 3, or 1, 2, 3, 4. In any case, any Hamiltonian is omega invariant should verify this relation here. That means this is mathematically how we can verify that the system is a rotation invariant when defined at omega. So if we consider omega equal 1, it means, for example, the angle is 0 or 360 degrees. So the shift matrix is also the X matrix, what we call it. And then the general form, the Hamiltonian matrix, can be written in this form. That means whatever the Hamiltonian 4x4, it should have this form here in order to verify the symmetry class X. How many parameters you have? You have one parameter is the energy. As I told you, they are symmetric, they are the same. All the quantum dots are the same. We have the coupling to the nearest, between the nearest quantum dots, and the coupling to the far nearest quantum dots. So we have 4 parameters. One, this is a complex. It has two real or imaginary part parameters. And then we have 4 free parameters, real parameters, free parameters. So any Hamiltonian that describes the system here has 3 parameters. And you know, as physicists, we always try to have the eigenenergy on the eigenfunction or eigenstate. If you calculate the eigenstate, it's shown that this eigenstate has this form here, as you can see. And this is linked to the regular quantum Fourier transform. I don't want to enter to the mathematical things, but the most important thing to remember, it's independent of this parameter, alpha, beta, gamma, and epsilon. That means this eigenstate are the same for every Hamiltonian in symmetry class X. What is changing then? Changing then is the energy. You can see that the eigenenergy is directly linear connected to all the parameters of the system, mainly the energy on the coupling parameters. And it can be inverted. What means that? What we have mapping 1 by 1 of the eigenenergy and the system. That means we can control the energy of the levels just by these 4 parameters, by changing the energy or by changing the coupling. So we have also the class Y. And if we consider the class Y, so this is mainly is pi over 2 rotation. So in that sense, we have another Hamiltonian, that is the second class. We have a Hamiltonian that should have this form here, general form here. And this general form, again, we have 1 parameter, 2 parameters from here, and 1 parameter. That's just we have 4 parameters. If we want to calculate the eigenstate, the eigenstate is also, it has this form here, but is independent of alpha, beta, gamma, and epsilon. That means independent of this parameter. Again, what is dependent of that is the eigenenergy with linear of these parameters here of the control parameter. We can control it. This means we have mapping 1-to-1 between the energy, the coupling, and the eigenenergy. We have, again, full control over the energy level of the class. In X and Y class, if we summarize, in the X and Y class, we have 4 parameters, and we have the eigenstate are independent of these parameters, and the eigenenergy depends 1-to-1 mapping to these parameters. So we have a full control for the class level X and Y. This full control over the energy level is prime motivation for our using omega rotation advantage. This is the most important that we have eigenenergy control, but eigenstate, eigenenergy control, but the the energy control, but the eigenstate we can is fixed, cannot change with parameter. We will see the advantage of that. So if you want to see it now more precisely, this is something nice here. We can build a Hamiltonian in this term here, and we can show that this from class X. We can also build what we call it unitary evolution operator V from the Hamiltonian H1. Why I told that? Because if you take T equal 1 or H equal 1, you can see that V is nothing than the unitary operation of evolution from the Hamiltonian H1. So what we learned in quantum mechanics, that if you have a Hamiltonian, thus you can build the unitary evolution operator from that. And you can also build another Hamiltonian from class Y. We have two classes, class X, you can have H1 on V. On class Y, we have this Hamiltonian H tier, you can build it. And also W is, we can build this operator, unitary operator, where the evolution now is the time one time is 1 over square. So a little bit crazy when you ask me why we choose that. It's a little bit trick. It takes a lot of time to get it. But the goal behind that is the quantum universal gates, to build quantum universal gates. We will show you. So V on W, first of all, they are quantum gates. So, but they are more than that. They are universal quantum gates. In order to understand what does the universal quantum gates mean, let's return to universal classical gates. So in classical computation, the universal gate is defined as a gate which can be implement or can implement any Boolean function without need to use any other gate type. That means this NAND gate, for example, is an universal gate in classical. That means your computer can be realized, or the operation of the quantum computer can be realized with NAND, or only, or not only. This is quantum gate. And in order to show you an example, here I can consider NAND, and I can build from NAND. Or, for example, I can build for NAND, and I can build other gates that I want. All the binary gates, I can build it from here, from this NAND. And I can build also from NOR. There is no problem for me to build one of them, NAND, or all the components that I needed in logic for logic operation. We call that universal classical gates. The same for quantum computer. In order to realize quantum operation, we have here two universal gates now. It's very famous. Sorry, very famous. The one here, the first set, is formed by Hadamard. Hadamard is the qubit where you can make a superposition of states. Formed by the phase shift, you can see that the space can be shifted with R, and what we call it control phase shift. And by swap, that means if you have qubits on another qubit, and you have a state of one on other, you can switch the state here to here on opposite. This is what a swap. You swap the state from one qubit to another qubit. This is the first universal quantum gate. The second one, you can use a swap again on what we call it a variant of C0, which is derived by this matrix 4×4. There's this gate on this universal gate. There are two universal gates, strict universal gates, what we call them. So now, V on W, our V on W was the question. Is it set of universal gate? Yes, we have shown that. How we do that? Little bit mathematics, but nice. This is the universality in quantum computation. If you want to build to show that V on W is a universal quantum gate, you should use what we call it a procedure developed by David Deutsch. So you can show that you can build from VW 16 Hamiltonian, etc. 16. Why 16? Because you have 4 by 4 matrix, you have 16 elements. And you can show, you can show from that this Hamiltonian built from V on W as combination of V, W on commutator whatever, that these Hamiltonian are independent. They have 4 by 4, that they have 16 elements. This Hamiltonian can be transformed in order to show that it's independent as super vector. Each Hamiltonian as super vector. You take the first column, you put it here. The second column, you put it here. The third column, you put it here. The fourth column, you put it here. You have 16 elements. Then you have 16 vector by 16 vector that has 16 elements. And you should show that the 16 Hamiltonian or super vector of Hamiltonian are independent. And you know how to show in algebra that vector are independent, just their determinant is non-zero for all these Hamiltonian H1 to H16. So with that, we have done it. Little bit tricky because we entered to algebra of what we call it algebra combined with complex, like what you call it Q square root of 2i. That means all the numbers that is in Q or combination was square root of 2 and I. And we can show that the solution never can, that's because in the characteristic polynomial, there's a combination of this. There is no possibility to have solution for pi. Pi is different, cannot be included in this system. Any case, this is more mathematics, just to give you an idea. But this is tricky, a lot of trick mathematics. By the way, we have shown that the determinant in general different from 0. What is the conclusion? Conclusion is this general set is universal. That means we can build anything. We could form any quantum gate, any quantum computation with the combination of VW. We call that V on W is universal. Okay, nice. Until now, we are in perfect system. We didn't see the errors. So the two others on this one are similar. You will build this one on the other is similar. What is the advantage what we have until now? That we have combined it in a definite way 4 quantum dots with symmetry and get universal gates. So now we go from hardware, if you want to understand, it's like in classical, you go from hardware to the software. You go from electronics for a combination of transistor to binary combination or logic gates. Exactly, we go now from quantum dots, we combine them when we obtain quantum gates. They are universal. But this is not enough because we should study also the effect of the errors here. So we should show that this system is better than 2 qubits and this is robust. Let's take this example here. And very nice. Suppose the system here, it has not exact values tau, but it's fluctuating. The value of tau fluctuating. This is the coupling, by the way. The coupling can be realized physically by magnetic field between. You can couple, for example, by magnetic field, the two quantum dots or whatever. But it's not constant. It's like little bit fluctuating. Or suppose that the energy of quantum dot is little bit fluctuating. So that means we have the energy and the coupling is a function of time. But suppose we allow us to have an interval of time, t, and we can measure all in interval in a large interval of t and see what happens. Okay, if you have large interval of time t, you usually, if you have fluctuation, you have the averaging and you have the finite value. Okay. Now, if you create gate, unitary logic gate like V on W, it will be also dependent of the average of these parameters here. Remember, the state of the system, they change the energy, but they don't change the eigenfunction. That means the gate V or W, it will only depend on the average. That means whatever the fluctuation here doesn't affect the function of our universal gate. We have stability against unbiased noise. Unbiased noise means that's the noise here has an average 0. That's what we call it unbiased noise. So that means if the fluctuating around the value of the fluctuation is 0, you have a value G, but you have average value in general plus fluctuating part. Okay, and if this fluctuating part is 0, then the system, we call this unbiased noise, and the system is stable against. That means there is no problem. No problem. The system is stable. Your operation is stable. It's totally different from the system doesn't have a symmetry. That's because of this symmetry, we are stable against this unbiased noise. But this is, we can consider that as classical perturbation. Now, transistor is protected from noise, unbiased noise, classical noise, if you want. But if non-zero, if you have G, for example, has G plus G0, then plus epsilon, but the average of epsilon is non-zero, is something like epsilon 0. So not problem. I can write G as G0 plus epsilon 0 plus a fluctuation. Okay, and I know this one is will fluctuate in 0. Once I know the average of it, just I shift it, so there is no problem. That means 0 or non-zero, there is no problem. Our system are stable once I know the average of our our basic points. Okay. Now the quantum error. We have done somehow part of the classical error. Now we can go to the quantum error. The problem with the quantum error before 2016 is hard to model, because in order to study what is the effect of the quantum error, we always try to understand how to model the quantum error in order to make the simulation. And it was the first tentative in 2016 to try to include the Pauli noises as a model for the quantum error. And it has again done more in detail on more proven in 2021. That's the Pauli matrices can be mainly what you call XYZ rotation, can be a model for quantum errors. And you can see here from this paper, we demonstrate that under randomization, that not we, that means the authors write, they demonstrate that under randomization, the experimental errors are well described by a Pauli error model, X, Y, and Z. So this is nice. This is first step, understanding modeling the error. And be sure that is describe it correctly, the experimental error, at least very close to the reality. Once we have that, we can use it in order to understand what is going in our system. Let's take our system here and try to understand what is the effect of quantum noise. Little bit, the procedure is a little bit complicated. Follow me step by step. First step, I will define as measure average fidelity. Average fidelity, you can understand that. Suppose that I send to my friend a photo, okay? If the photo is the same, is a totally copy, there is no difference between the photo that I sent to my friend and what he received. Clarity, perfect, nice, nothing there. All elements are there. We call this fidelity is 1. 100%. I sent 100% copy for my friend for the image that I have. I have fidelity 1. My image the image that he received is fidel 100% to the original. Suppose that I sent the image, but because something a little bit happening, some error in bits and so on, so in pixels, some pixels is not clear, changing color, whatever. So they have lower fidelity, less fidelity than 100%. Can be going less and less to 0%, what is unfidel. The image is totally different. So we will consider the fidelity as measure for our functionality. If we have 100% fidelity, we are okay, we are good. There is no problem with the quantum errors. If there is a fidelity low, there is an error. Always, yeah, we are thinking that the fidelity will be reduced with the computation time or computation length. So now let's try to compare the two universal gates that we have with the new universal gate V on W. So And then we can take 2 errors, not 3, the x on the z rotation. In order to understand what is the x on z rotation physics, is one when you have, for example, a flip of qubits. That means the qubit, this qubit flip to 1, or this qubit flip to 1. Okay? This is not problem because that can happen. For example, you absorb on opposite way, in one direction or other. For example, if you have 2 level atoms, you absorb 1 photon, so the system coming here, thermal photon, or the system emit one photon. So absorb or emit, you will flip the state from 0 to 1 or 1 to 0. Thus, X rotation can be understood. That's just you absorb 1 thermal photon or you emit 1 photon. That's it. So the second part from the error, because the system is not stable, it can be the cavity. If you have a cavity or an ensemble of atoms here, the cavity influencing the state on giving some phases for the 2 states here. Okay? So the cavity is somehow when it close to atoms or qubits in general, it can include phase. And this is the second type of error. That's X on Z. I didn't speak about Y because more complicated physics, but this can be easy to understand. And let's use this error. So what we do, the idea is the following. We take, in order, suppose that we have algorithm. Algorithm, what is the algorithm? It's combination of quantum gates. Just I will put operation of quantum gates one after the other. So if I want to have general, to describe general algorithm, I should choose randomly this gate. That's what we do. First of all, I choose randomly V on W in the first step. And then I should include the error, but the error could be randomly also. I include one of the other randomly. Okay, then the first step, I have V, for example, and I have error, the error epsilon x. Okay, and the second step can be V on W, and for example, the error epsilon z, and so on. And do it 400 times. That is 400 steps. Each step represents for me an operation. Is the time, I have time here, the first time, t equal 1, 2t equal 400. That's what I have here inside. Okay, then I do it for all the 3, for this, and this. What I have here, I have random, but as I represent one random algorithm. It's exactly what we do in Monte Carlo simulation. We take randomly and repeat the process several times. We will do that when we repeat the process several times. The first one repeated several times, thousands or millions, whatever, and make the averaging after. And that's give you the, and we calculate fidelity every time and make the average. This is the average fidelity. And we compare average fidelity. That means if the fidelity is closer to 1, that means the error, it doesn't affect or has or effect very, very small. If the fidelity reduces, that means the effect of the error is more or more clearer. And you can see here that the blue is our system. This is our system, the blue. The green is the third system here, and the yellow is the second system. In any case, you can see that the fidelity after 400 is closer to 1. So that means our system is very stable compared to the conventional, or you mean what is well-known universal case. That we have done for 2 errors, 2 types of errors. But it's not fair to compare just for two errors. We know that we have 3 types of combination of them. So we have done also to the combination of 3, X, Y, and Z on combination. We can have error, combined error, X and Y in the same time. We have 15 possible errors. But we suppose that the distribution is equiprobable. That means we take every time probability of the error 1/50. That means we take 1/15 ensemble. We repeat the same procedure with this, and compare it to the same procedure that I've mentioned. Again, I take randomly V on W, I add one randomly one of this error with probability 1 of 15, and then I build the first step, second step, and so on, 400 step. And then after that, I repeat the procedure thousands of times and make average of it. And I calculate the average fidelity. You see the average fidelity is little bit lower than 1. It's the fourth or fifth order, lower 10 minus 4 to 10 minus 5. You can maybe 10, maybe about 6, but means I can conserve my states on that the calculation, and I trust my calculation more than 400 steps because my algorithm is 400 steps or more. Here you can see that the other ones is reduced, and we can say with little bit confidence that our system now is more robust against the quantum noise compared to the conventional quantum universal quantum gates. And then third one. Now we take the probability, the 3, but with different probabilities. We say, for example, for X on Z, we have probability 3 over 31. And for the others is 1 over 31. And we do this. That means we are a little bit biased against X on Z. We have more, the system has more errors in direction of X on Z. Remember, X, that means flip of the few qubit, or Z, what means phase, we include the phase to do the cavity phase. As you can see from here, it seems to be that the third and the 1, they are very close. As well, 400 computation. We have done more than that. We have done the processor for longer than that. And for longer than that, our system is much stable than the green one. That's I cannot show because it's too lengthy, but just believe me in it, because we have done that on simulation. The referee asked it several times about it, and then we get like 2-3 times between communication with the referee, asking for details and so on. We were able to work in details about it, and thanks to this, we have spent 1.5 years in order to, from submission to paper, publish it, because a lot of questions that improve the quality of the paper, sure, and give us hard time to explain all the things in more detail. But after that, we were able to understand. Sometimes the question of referee is very constructive, even they are sometimes very, what they call it, picky. So now we have done the first. But what if the quantum dots are not the same exactly? What we call it asymmetry. We have some asymmetry, because in industry, we cannot construct exactly the same quantum dots. We cannot realize the same coupling. You can see, for example, we can have asymmetry due to the energy. The energy of one of them is not the same as the others. Or we can have also error in the coupling. We have one is coupled a little bit more than the other, to the nearest coupling, or the far nearest from here on here, for example. So what's happening? Yeah, we can tolerate to 1%. Usually we can realize 1%. Usually the error is 1% to 1,000, 1 of the thousands. That's the possible error can be realized in when we can realize practical system. When we do that, we can see the most important thing, the most interesting thing, that's the fidelity, the average fidelity is still with just a variation of 10 minus 5. That means the fidelity is almost constant, is stable against the small asymmetry. That means we can practically realize the system, even we shouldn't very, very careful to be perfect. No, we tolerate some error from industry, no problem. And the system is stable against this error coming usually from construction, from industry, or from construction of the quantum dots, of how we realize the coupling, and so on. So let's summarize what we have done until now. Again, we begin with a 4-core system using the omega symmetry. Then we have construct universal gate, which can be used for computation. But we have shown that this universal quantum gate is robust against error, classical error, quantum errors, and static asymmetry errors. So more than that, we can show that this system is stable against the decoherence time. And within the decoherence time, we can memorize the state 1,000 times. That means we can do 1,000 calculations. We can memorize on doing 1,000 calculations because we begin to lose the information. It's very important. Quantum memory is how you memorize a number. Let me tell you an example. Suppose that I will give you my phone number now, whatever, 573, etc. And I will tell you, please memorize that. That is your memory, temporal memory. And I will ask you to do some operation. And then after that, I return it to you and tell me, please, your my phone number. Usually people will forget it within a few operations. If you do for like few seconds, after few seconds, a few minutes, they will forget. The ones that they have very nice or big memory or nice memory, long memory, but the ones that they are able to do calculation, after that, they are able to give you the exact phone number. And this is the same. For here, we have the same. We have a system that we can memorize a state. We do a lot of calculation. And then after that, we can do to the 1,000 calculation. After that, we can ask what is the initial state that we saved. On this is very nice because we allow us to do calculation on computation within the T-coherence time, because the T-coherence time is hard to control. Okay, so very nice. Now, very nice what we have what we call this quantistor. So this quantistor is stable against error. We can use it as quantum memory and so on. Now, we have the concept of scalability. What is the scalability? So to explain the scalability in easy way, I will say the following. In classical, let's go to the classical computer. The classical computer is based on transistors, on combination of transistors. That would give you the classical computer. And usually you have an error. It's very small error. But because the error is very small, you can combine several transistors, and you be confident that your computer can do the calculation with almost negligible error. We speak about scalability. That means we tolerate some error, very small error, and we can, from that, we can build a classical computer. Scalability in quantum is the same. You have building blocks for us as transistor, and we can combine the transistor with other big number of transistor to other, and then we can see that is tolerable. This is what we have shown, that the system is scalable. This is definition, more details here. I don't want to enter this, how we define the scalability, what is the error, maximum error tolerated, and so on. That is more details here, but in conceptual way, if we have very low transistor error, and is stable against the classical quantum error. And if we combine the transistor together to build the quantum computer, you can see here a combination with a transistor, and we can hold the error small with a big number of transistors. Then, in that sense, we have realized what we call scalability, which is really a problem for quantum computing. It's the big problem for quantum computing. Now, we can, so I told you we can realize quantum computation scalable grids of 4-level cores. And from that, what we have done again from four quantum dots, if you want. It can be any other system, but this is with some same symmetry. We have created quantum gates robust to the errors. We have the scalability. So we have here realized what we call it blueprint for scalable universal quantum computation, but using 4-level system. So I conclude, but the conclusion with bit length, because I will continue to the level where the science is now, because we have done this work on published it by end of December. That means more than 1 year, December 22. Then we have like one year from now. In this work, we have put forward the blueprint for scalable universal quantum computation based on transistor. we find significant robustness against the error, classical and quantum error and asymmetrical error. There is another advantage of the transistor that we are working on is to use it in quantum cryptography. So that's since 2000. People know that quantum cryptography is traditionally based on two-level quantum system. This paper said that a protocol based on higher dimension system presents an advantage for legitimate user to detect the spike, quantum spike. That means higher level of quantum system give more security and for the quantum cryptography. And this is what this is also transistor obviously has multi-level system and can be used maybe for quantum cryptography. We are using this quantum for the transistor not on for the quantum machine learning, because we can manipulate the parameters and we can use it as a component for quantum machine learning. That's what we are doing now. We are doing, to be honest, we are doing that in collaboration with my colleagues to really use our transistor as a building blocks for quantum machine learning. So all this work is done, as I told you, 1 year ago. We began like more than 3 years, and then we submit the first version in 2021, middle of 2021, published by December 2022. Takes 1.5 years in order to respond to all questions from the referee. That's improved totally the paper, but you can see that the paper is lengthy, it's more than 22 pages. I was trying to avoid to give you more details in it, because there is also physics and how to realize the coupling, how there is a lot of details, mathematical and physical details I was trying to avoid, or maybe a little bit superficial in this form here. Most important thing here, and very nice, is the following. In 2023, exactly 1 year after a publication, people spoke about randomized benchmarking experiment. They have a randomized benchmarking experiment. What they discovered? They discovered that they validate the Ququarts. Ququarts is a 4-level system as a feasible tool for quantum information processing. So that is also they validated the fact that the Ququarts experimentally, if you want, is really a valuable and valid tool for quantum information processing. It has a lot of advantage. So in August 2023, people speak about also another paper. And this is prestigious paper, PRX. Again, they are speaking about using realization of 4-level system with a transmon, and that has an application to near-term or long-term hardware. And again, this is the conference recently in March 2023. And this is, by the way, this international conference on architectural support for programming languages on operating systems. You see that is a little bit different field. People is concentrated about software and so on. And we see that people working on qubits, on for programming languages and so on. And you see that there is their conclusion is we extend qubit combination scheme consisting of both qubits and Ququarts, that's 4-level, reducing circuit error by 50%. That means that is by combining qubit and Ququarts, they are able to reduce the error circuit by 50%. They have done it. And then this can increase the computational space available by 2 times while maintaining circuit fidelity. That means the fidelity will be the same. It's not changing the quality of the information. So with that, thank you very much. And I hope that you can, I was trying to be little bit superficial, not deep, to explain all the details of the work because it's too deep and takes a lot of time, but at least to give you an idea what is going on, what is the importance to go behind or beyond the two-level system qubit. Okay.